Okay, so this is going to be a rather short lecture because this topic, at least the introduction to this topic, is quite simple. I don't really have to teach you much theory. So we'll do this. I'm going to give you a bunch of questions, but maybe also I can open the floor to questions about, we can do some more applied optimization or related rates questions if you want. But this shouldn't be too difficult. Okay, so today we're going to start basically our adventure into the second half of this course. All right, so this course has already been broken up for next year. So this 134, you are in the last 134 full year course that is ever being taught at this university.
I wish I took two different courses. Holy crap.
You wish you took two different courses?
Because I get two different marks.
He's been doing it.
I have two different attempts.
Yes, George has been doing it.
I can't take, I have to do both of these courses in one attempt. I mean, like it's as if these are two different courses taken in one full year. I have to do one attempt for both courses instead of a separate attempt for each course.
Basically.
Okay, in any case, you're in the last full year course. Next year, this is going to be broken up into two pieces.
Are you saying this to make us feel worse?
Differential calculus is going to be the first half of the course, and integral calculus is going to be the second half of the course. So integral calculus is hard. I don't mean to make you feel bad, but differential calculus is very straightforward. Right? It's very much, here are the rules, apply the rules faithfully and you'll get the answer. Integration is very much like pray. Pray and something will hopefully come out of this. So it's going to be much more, you're going to have to really get in the mode of accepting failure and trying something else. Right? You'll work out not like failure in the course. Like I'll give you a question and you'll fail to do it, and then you'll have to try again. Right? So you're going to have to get used to throwing away old work and starting again. And it's going to hurt, it's going to kill you, right? Because you're going to feel like you're wasting so much time. But that's the only way to do it. All right, so watch this. Shh. Great. Okay. So we're going to do this backwards, because when I taught you derivatives, we started geometrically and we ended algebraically. So we're going to flip it now. I'm going to start algebraically talking about integrals, or in this case, antiderivatives. And when we come back from the break, then we're going to talk about what integration means geometrically, which is basically the fundamental theorem of calculus, right? Which I'm going to give you a full lecture on. I'm going to give you a lecture where you're not going to have to understand anything in the lecture. I just think the fundamental theorem of calculus is so important that you should see it. Yeah. Antiderivatives may be on your second test. Not integrals. Integrals are kind of different. Right? So an antiderivative is going to be something quite simple when I'm talking about it today. Integration generally will be something of a different matter. You'll see what I'm talking about and why you shouldn't be too afraid of what's to come. Okay, so I'm just going to give you a definition here for antiderivative. Okay, let f of x be a differentiable function. Okay, big F is called the antiderivative of f when, and here's the property, the only property that we care about, the derivative of f with respect to x is equal to the derivative of f. Jesus, Murphy. No. The derivative of f with respect to f is, the derivative of big F with respect to x is equal to little f. Now, this provision that we denote the antiderivative as the capital of the original function is not like universally applicable, right? You are not to think when you see a capital letter that that's the antiderivative of something. For today's lecture, I'm going to use capital versions just so I don't have to write big F is the antiderivative of f every single time. That's going to get cumbersome. So for this lecture, we're going to tie together functions and their antiderivatives using this type of notation. Okay, so this is what we're looking for, and I bet you could already do some. So if f is 2x What is big F, the antiderivative of f? So we're looking for a function whose derivative is 2x. What's the derivative of this? Okay, that's anti-differentiation, right? In a nutshell. Right? You just have to sort of find the function whose derivative gives you the thing that you're looking for. All right. I know that seems easy as stated, but in practice this becomes very difficult. So for example, that doesn't have an integral. That just outright you will not find a function whose derivative gives you that. There's no way to tell ahead of time that that's the case. The proof to demonstrate there is no such integral is extremely complicated. But look, already something that's impossible and unpredictable. Right? So I'll show you, because in your, I gave you some exercises at the end of here, and I snuck in 2 impossible ones that look like they should be possible. Right? So this is why integration will be hard. Right? Okay, let's try another one. What about this one? If g of x is cos of x, what is big G? What function do I take the derivative of that produces cos of x? Sine of x. What about something a little bit harder? 1 over x plus 2e to the 2x. What is big H? Yeah, do it individually. So what's the antiderivative of 1 over x? Ln of x. What about this guy?
Same thing. 2e to the.
Just e to the 2x.
Wouldn't it be plus 2e to the 2x? Oh no, it's
The chain was on
zero,
top.
yeah.
It's multiplying the 2, right?
You should never get an integral wrong. That is to say, if you claim you have found the integral, antiderivative. It's literally the only class where I'm going to use this terminology. We'll change to integral come Monday. But you see, if you claim that this is the antiderivative, all you need to do is take the derivative and confirm. Right? So on a test, if I say find the antiderivative of this, you better well check that the thing that you found, its derivative goes back. And that you can integrals are totally trivial to check your correctness. Just like this, just take the derivative of it. What do you get? Cos of x. What do you get here? 1 over x plus e to the 2x times chain rule, which is a 2. So they may be hard to find, but they're totally easy to confirm that you found the right answer. Okay, but note something. These were not the only antiderivatives. I was going to say that, antiderivatives. Right, why did you say x squared was an antiderivative, but what is x squared plus 7 prime?
Oh, it's also 2x.
It's also 2x.
Well, wouldn't you?
Yeah, you got it. What about cos of x plus 10? What's the derivative of this? Sine of x. Okay, so that was an antiderivative, but there's many antiderivatives. How many antiderivatives do we have for a single function? Infinite amount. Why? Because you could just arbitrarily, constants, when you take the derivative of a constant, it turns to 0. Right, so you could throw any constant you want. So does this make sense to us geometrically? Well, let's take a look at the parabola. And let's say that this is the parabola that goes through 0, 0. Let's put one a little bit higher. Let's put one a little bit higher. Okay? So imagine these are the same parabola over and over and over again. So what's the slope of the tangents for the base parabola? The parabola is x squared, so its derivative looks like what? 2 of x, yeah? 2x, that means I have to go a little bit higher. Right, so if these are f's, a family of functions, this should be f prime. But notice, this tells you about the slope for any of these parabolas. Right? All of these parabolas have derivative that looks like this. Right? For instance, if I go here, if this is x equals 2, this is telling us the slope there should be 4. So if I go to x equals 2 here, the slope at each of these parabolas is going to be 4. Right? So there's going to be a family of derivatives, a family of functions whose derivatives give us our target function. So more generally, we call f plus c, right, such that c is a real constant. We call f plus c the general antiderivative of f. Okay? Now, from now on, when I say antiderivative, what I mean is the general antiderivative. Yes?
Isn't that supposed to be negative sine x? I don't know, is it?
Oh, did I do this backwards?
'Cause the
What's
first
the
one.
Oh, yes. Sorry, I switched this. Yeah, I switched this. Thank you.
Okay.
That should have been sine of x, and this should be cos of x. Thank you.
Yeah.
Okay, so this is the general antiderivative of f.
Good.
Right? So if we have f equals 2x, this means that the general antiderivative of f is 2x squared plus c, a constant, such that c is a constant. Okay, so because there's an infinite amount of functions whose derivative can give you f, we have these type of problems called initial value problems. So these are a category of word problems. I think it's technically in your syllabus, so we can ask you an initial value problem. They appear all the time in science, so they are quite important. But I'll show you how they work. So it's basically, we say, find the singular antiderivative of f is equal to 3x squared. Find the antiderivative big F of f is equal to 3x squared, such that f of 1 is equal to minus 1. Okay? So this is a constraint on the problem. All right, so now, given that the antiderivative is constrained, we actually can find the precise f that has this property. So like in physics, they can basically say, let this be the velocity and this be the distance, and then work something out. But in any case, let's solve this one. So what is the general antiderivative of f then? So if f is 3x squared, whose derivative gives me 3x squared? So give me an f such that f prime is 3x squared. Okay? Yes, x cubed. That's actually not too bad. Okay. The general antiderivative, though, means we have to have plus c, such that c is a constant. And now we can use our constraint. So we know that f of 1 is equal to minus 1 is equal to 1 squared plus c. So this means that c is, did I do this right? F of 1 is minus 1. 1 cubed. Okay, so this means that c is minus 2. I think I wrote 0 in the notes, which is wrong. Sign error. Okay, so this means that the f for this one, and this means that the singular antiderivative in this case is x cubed minus 2. Right, so you can always get, if we give you a constraint, you can actually find the actual specific antiderivative for this problem. So don't forget to try a little bit of these initial value problems. Okay, so let's try some now. Find the general antiderivative for, and I'll give you a bunch. So f of x is equal to x to the power of 5. G of x is equal to 1 over square root x. Sine of 2x. Whoops. H of x is equal to sine of 2x. And finally, let's try I of x is equal to 2 to the power of x. So in each of these cases, I want you to find the general antiderivative I, H, G, and F. Give that a go. Now, going backwards, you're going to have to get used to it. So the basic strategy, the one number we use, well, it happens to 6, 6.1 at the time. But then you know the 6 is going to come down. So usually you're going to have to go to 6 twice per 6. You should be able to write the generals for taking a derivative of mononomial or something like something to the power. So the antiderivative of x to the power of a is a on x to be a plus 1 divided by a plus 1. That will come down and you need to cancel it immediately.
What's hard is going backwards. My brain doesn't work. I just don't know what, it doesn't click.
No, this is a number.
Well, that's the easy one. Now the other
This is number 2. Oh, it's easy. It's just, it's x power of -1 over 2. It would have been 1 over 2 and then 1 over 2 times 1 over 3. Because it's x to the -1 over 2. It's just 1 over x over square root. Well, none of them are able to do.
Wait, half of the power. That's half. That's right. Half x to the power of right?
What if you become -1 over 2? Which one's the antiderivative?
This is the.
No, which one? That's the antiderivative. So if you derive that.
Yep, so bring it down. Oh, what the heck?
Is there like some secret trick to it that we don't know? It's guessing.
Wait. What gives me one? I mean, what gives me one? Yes. So why does he say it's a quarter? Why is it a quarter?
Half times half.
Wait, I have
Half plus half.
Wait, so how do I get this to be one? What? So confusing. Okay.
Okay, so that's very close. Here's what you what do you get?
He's like, okay, I'm ready.
Sine 2x.
Dude, I'm
X is a stand-in for whatever happens to be there next time, which may, in this case, was 2x. So that's why I try to encourage you to. I try to encourage you to see these as abstractions. There's like the derivative of this.
So wait.
So this is t pairs multiplied by. So the mathematical way of writing this is actually with that
Minus 1
somehow
comes
confuses underground. But like the intention is this x is just whatever. But it could be
and
the difference plus 1 at the top. We're just using these things to say something like whatever it happens to be your application. So in your other example, x this one.
I know number 4 has a key in it. That's it.
is there somewhere you can generalize it?
Yeah, I know that. It has to be
That's just like, yeah, just error.
Okay, let's take these up. You didn't get a single one?
I got half of the last.
Who got at least one?
Okay, I think I got.
Turn around and feel shame.
You did have to make me turn around and feel shit.
Huh? You got all of them. Well, you had some practice. Okay, let's look here. Okay, so what derivative do we need to take to get something to the power of 5? Let's just start like that, right? Yes. Right. So if I put something to the power of 6, right? We know when we take the derivative of that, the 6 will become a 5. That's the rule, right? Actually, what's going to happen is we're going to get 6x to the power of 5. So what I just have to do is make sure to divide by 6, and that will get rid of it, right? So this is just 1/6 x to the.
Is there a way we can generalize this?
No, it's integration. Well, I can generalize that statement,
Oh, okay. But
right?
not every
But not every. The problem will be we can't take integrals over products, or integrals over divisions, right? See, but I have given you rules, every rule for differentiation, right? So now you guys are going to appreciate it that differentiation is the outcome of a very rigid algorithmic process. Integration, I only half facetiously say you have to pray, right? Because I'll show you a fun little cartoon when we begin it.
Can we just use those rules we got for to find the derivative to be able to find the integral?
I tried.
Yeah.
Well, look, I can say the antiderivative. The antiderivative of x to the power of a is x to the a plus 1 over a plus 1.
So is it that? No, but that's
Sure, but you don't need that as a rule. You know how to take derivatives. So that's just the other side of that equal sign.
okay.
Yes,
So is that the?
you tilted this. Well, thank you for telling me. Yeah.
Is this? It's only for this specific one. You can't do this for the other one.
Very much you pulled me. So that's the deal we made. I won't be angry. Okay, so
If we did x to the negative 1 over 2.
what about this one? What derivative do I have to take to get 1 over the square root of x? Yeah.
Ln of the square root of x.
Who says ln of square root of x? Okay, so I'm going to entertain that. So we're going to say, I'm going to put a question mark over here. Mainly because you're wrong. But I'm going to entertain this, right? Right? Because you should always check, right? You should always, if your claim is that the derivative of this is this, right? So I can check this. So the derivative of g is what? 1 over the square root of x. Looking good so far. But what do you got? Chain rule. What happens to this
Oh,
guy?
I meant multiplied by 1 over root x. That's what which is.
Okay, so you mean ln x times 1 over square root of x? Aren't you going to generate a product rule?
No.
Yeah.
No, you're misunderstanding.
I'm misunderstanding. Okay, so did I write this correctly? You are claiming this
That's
is
not the right answer, but.
that's not the right answer. Okay, so
Sorry, from here.
do you still stand by this? No. Okay, let's try a different one. Yes, sir.
So here's the thing. I use this. So it's negative 1 over 2.
X to the power of negative a half. Is that what you're saying?
Now this thing.
No, that's x to the this is x to the power of a half. Oh, I see. You turned it into this to just basically undo it. That's fine. Sure. So, okay, that's not a bad idea, right? Because we need to take this guy
You want me to write down?
and then add 1 to it. Hey, pay attention to this so you don't ask me questions about this. Right? Okay. You have to add 1 to the top, and then we know that this is going to come down, so we're going to have to divide by it, right? So we're going to have to divide by a half. That should work out. So let's just try to simplify this a bit. Well, this is just x to the power of positive a half divided by a half. That ends up being 2 root x. We'll just take the derivative, and you'll see it'll go back, if you don't believe me.
2 root x.
If you take the derivative of this, you're going to get 2 times 1/2, 1 over square root x. Yes, sir?
Let's have the plus c to the f.
Oh, yes. We should be adding plus c here every time.
We have to write CER every time?
I write it because I want to say, look, this c is a constant, right? Because remember, I've been agitated about like not understanding the difference between independent variables and dependent variables. Like when I write this, I'm trying to say, look, don't treat this as like something that can move. This is fixed. Or I don't know what it's going to be fixed to, but treat it as fixed. If we have to take the derivative of it, it disappears. It's constant. And so you don't have to write this, but it's a good habit to write it. Right, so you don't get confused. There are other instances where c was the thing moving. In your midterm, for example, c was the independent variable. Okay, so that one ended up being, I'll just remove that derivative. H, what about h? Sine of 2x. Okay, so this is how I would do it. I just need a little bit more room, so I'm gonna. Okay, so I see I have a sine. What function produces sine when you take its derivative? Okay, sure. We'll say negative cos. Okay? So I look at this and I say, okay, this is pretty good. So what's the derivative of this?
Negative sine
2 sine 2x. Right? Don't forget about chain rule. If there's a 2, is going to fly out of here. Okay. Let me do this. But if I take the derivative of this, you're going to get minus sine of 2x times the chain rule, which is going to end up being sine times 2 times of 2x. Yeah, okay, so I'm very close, right? So this is not the antiderivative of this because of that lingering 2. But that's easy to deal with. So like you have to be very good at differentiation in order to integrate, right? Because you have to basically undo a process. That's why it's a little bit difficult, right?
I wonder if it's same.
Then you just multiply that by half.
It's definitely the hardest one on the board.
Oh.
Well, let's recall, what is the derivative of 2 to the power of x? So if you don't remember, you should have worked it out. You do a very simple implicit differentiation and you'll get it. You'll eventually get it to, well, should I just work it out? Yeah, I think maybe. Okay. Okay, so like we're stuck. So in my own notes yesterday, actually, I had to work this out because I forgot. So I want to let y equal 2 to the power of x, and I want to know what the derivative of y is, right? So I'm going to do it like this. I'm going to say ln of y is equal to x ln 2. This means that 1 over y prime is equal to ln 2, which means that the derivative is 2x ln 2. That's how we worked it. So the derivative, well, we're close then. Isn't this almost it? Like we're trying to get 2 to the power of x, right? There's the 2 to the power of x. There's a 2 to the power of x here. But what do we have to adjust for? The ln 2, right? This is a constant, just like 6. So that's too much. So all I got to do is say, well, it's 2 to the power of x, but let's just get rid of that ln 2 in the very end. So if you don't believe me, just take the derivative of I and see that you get back little I.
Oh, because you wouldn't do quotient rule because it's like an actual.
No, there's no quotient. We're going backwards now, right? And plus quotient rule doesn't apply to constants. Yeah. But like that's basically the problem we're going to have. There's no way to undo quotient rule or undo product rule. There's something kind of like it, this integration by parts, but oh my God, it's going to get so complicated. Oh God. We'll get there together. I'll try to train you as well as I can.
Is it plus C as well?
Oh yeah, all of this should have plus C. So you will definitely get dinged for this. No, I got dinged for it. I always forget it. But it's important. For the initial value problems, you need to put those C's there. Okay, so let's try something else. All right, so given that you just did that, let me give you one more to try. Basically, just to distract you while I wipe down the boards. So give this one a try. F of x is equal to 3 over root x plus sine of 2x. Find me the antiderivative of that.
I don't know. I just started today. What do you want from me?
I'll do a lap. Have you guys done it already though?
I haven't tried.
Yeah. Yeah, because you've already done the pieces themselves. I'll come take a look.
Hey, Professor,
Yes, sir.
that's the right answer.
Well, I'll come check.
When x is like this, it's pretty easy to use that formula. But that's the only.
Oh, no, I must have a
Is it this? Because it's just like.
It's brutal.
Yeah, no, I did.
Yeah.
Because it's part of the thing. You just leave three at the top. Yeah, you didn't figure it out. Yeah. So this, since it's in the denominator, it's dividing it. It's as if it's times 2. So this becomes what? 3 times 2 equals 6. And then you subtract the 1. Or you add the 1, it's not a subtraction anymore to the top. Because we're working backwards. If we're taking the derivative, we're subtracting it. It's n minus 1 here. But if we're doing it backwards, it should be n plus 1. I'm so proud I got this. Like, right.
And then, yeah, that's the chain of everything.
That's the first part.
And then there's the sign.
because on a midterm, you're going to feel like shit when you get something like this wrong. Because you'll just say, oh, I could have checked it. I may actually give you, maybe I'll give you guys points on the midterm for checking your answer. Or maybe like 1 mark I will give for determining your answer is correct. Yeah, but then half of you will panic when it doesn't work.
9 marks out of 10.
Or that's just like, that's sort of shitty because that's an extra mark for people who get the answer.
Yes, I just realized that.
I think you guys should think about if you want me to do that or not, right? Because it's going to benefit those people who are already doing well and hurt those who aren't. Okay, so I'm just going to give you the answer to that. This is just basically the same. We've done these individually already. You shouldn't let that 3 really trouble you. So this means f is going to be, so it's going to be the square root of x. So when I take the derivative of that, that's going to go to the bottom, but it's also going to pop out a half, which means I have to get rid of that half with a 2. That's going to be a 2 times 3, and then minus cos of 2x over 2. Okay. So the last thing I'm going to do today is just introduce a piece of notation that is going to prevent me from having to like say, oh, we want the antiderivative of f in this case, because that would be way too long to write. So here's your new piece of notation. And if you want to start panicking, I'm okay with that. Okay, so here's the definition of an indefinite integral.
Like to each term? There's always plus c, because there's the answer to the first fraction. It's going to be 0.
This is going to be equal to the general antiderivative of f of x. Right, so I don't have to say each time, let capital F be the generalized antiderivative of f. That is now codified into this statement. Right? So this is basically saying what this is equal to is the antiderivative of f. Okay, there's like, just so we can talk about this, these have names. Okay, so this is called the integral sign. This thing in the middle is called the integrand. And this is called the variable of integration. Because, yeah, remember, we can take derivatives with respect to whatever variables we want. So we can undo those derivatives with respect to whatever variable we want. All right, so just to show you how this notation works for what we just did. All right, so I can write the integral of 2x plus 5 dx. That's going to be x squared plus 5x plus c. See, now I don't have to go through this whole such that c is a constant. Okay? I could also say something like, integral of cos of x is equal to minus sine of x plus c such that c is a constant. Okay, so like this is just, at the moment, notation. So I don't have to say antiderivative anymore. So I'm going to say integral now. Integral and antiderivative technically have the same type of distinction as taking a derivative using algebra and taking the derivative using limits. So we're going to have to discuss what the geometric interpretation of this is. Deeply interesting, but it's going to require a bunch of development. What else do I got for you? Okay, so I'm going to write down on the board 10 problems. 2 of them, well, one of them is hard. Another one of them is outright impossible. Right, so they're hidden. Yeah.
If it's impossible, does that mean it can't be differentiated?
No, everything can be differentiated. Everything can be differentiated. But it may not be possible to find a function whose derivative gives you your target. Right? But that's why differentiation is nice. This is a well-defined operation that works in all instances. Integration may or may not work.
Can we get that on the test? An impossible
My high school teacher did that by accident.
by accident?
Gave us an impossible integral on the test, and I wrote that. I'm like, you idiot. I didn't write that. I wrote, this is not integrable. I want my marks back. And a different high school math teacher. Okay, so this is your permission now. Talk, get coffee. I'm going to write some stuff on the board. We're going to work on it for the rest of the class.
It starts on the Tuesday of next week. It goes from the 19th, which is kind of the day we get back. Hopefully I'll have like Wi-Fi here. That's it. I'm like, die.
One moment.
You can probably. The antiderivative. Yeah. When were you getting the most trouble? At what rate of change are you getting from silver to trouble? Using actual calculus. Yeah. How fast are you getting from at 12 p.m.? 12 p.m. Dude, I'm gonna be free. He's lying. My dad's lying. I like to stretch my legs. He was like insulated cup and he puts like a gin and tonic in and like sips on them. Not even there.
Yeah, but the longer you wait to tell me, the more irritated I will be. Right? As long as you give me an opportunity to fix it, I don't care.
I don't think on purpose.
I know you don't do it on purpose. That part isn't on purpose. The not telling me part, that's on purpose, right?
This is. Intruder, bro. Khan Academy for the win. I ain't got money for that. That's hilarious. That is so. What do you get? What do you get?
Is the lecture over or is it just these exercises?
Yeah.
Lecture's
It's
over.
Like this equals over 2x squared. Genuine? No, that was like my genuine question at first. I'm like, what do I do? Like and subscribe. Is it? It's 1 over 2x squared. Right?
Like and subscribe.
Oh, it's for the YouTube folks, you know?